Our next presentation is going to be interesting. It's the alternate sources for fly ash, and Rajablpour, a professor from Penn State, was unable to make it here, so we're going to try to do it by phone. He sent us the presentation, so you'll actually have it on the screen, but he is going to be speaking through his phone. So we'll see how this goes.
Okay, fantastic. So good afternoon, everyone. I'm Rajablpour from Penn State University. Can you all hear me okay? Okay. All right, very good. So let me start by thanking John and Rick and Cindy for organizing the conference every year, and also for inviting me and my students, and also apologize to you guys as well as the audience for not being able to be there physically. I was really looking forward to the opportunity, but as I started driving down about 7:30 this morning with two of my students who were supposed to present posters, but we drove about 10 miles out of State College, and we realized there is the roads were in pretty bad condition, and we figured that there was no reasonably safe way that we could get down to Harrisburg. So I'm hoping that this phone presentation would work okay. As the title of the presentation suggests, I will be talking about alternative sources for fly ash or for pozzolans in concrete. The last few years, we've been doing research on unconventional pozzolanic materials, such as off-spec fly ashes, landfill fly ashes, and some other types of pozzolanic materials like calcine clays, which I'll talk about today briefly. And these kind of stem from the challenge and the kind of spreading issues with regards to the shortage of high-quality conventional pozzolans, such as conventional fly ashes, which I'm sure a lot of us in the audience would have experienced this in Pennsylvania and in the Mid-Atlantic region, but it's not just limited to our region, and it's really an issue that is felt in many parts of the country. I also want to acknowledge the financial support of American Concrete Institute, Pennsylvania Coal Ash Research Group, and York Building Product for funding this research, as well as the good work of Mona Zahidi and Kash Jafari, who are graduate students that are working on this. We can move to slide 2, please. As a motivation, we know that supplementary cementitious materials, or SCMs, are an important ingredient of concrete. We use them primarily to improve the durability, also to improve the sustainability of concrete, reduce the carbon emission or carbon footprint of concrete. Sometimes we use them for improving workability of concrete, and traditionally we also use them as a means of lowering the cost of concrete because they have been cheaper than Portland cement. Although this has become less of a fact these days, as at least the high quality conventional pozzolans become in short supply, their costs have increased. So there has been recent issues with the availability of fly ash and slag, which are the most common SCMs. The graph that you see on the right side is from American Coal Ash Association, which shows in the blue curve the production of conventional pulverized coal fly ash in the U.S. over the years. And we can see that since 2008, somewhat in the middle of the graph, till today, the production of fly ash has dropped by more than 50%. And this is primarily because of closure of many coal-powered power plants or coal-burning power plants, and also conversion of such plants to natural gas, or some of these plants to natural gas fuels. Also, there has been some air emission regulations that have come into effect over the last 5 to 10 years, which affects the quality of the fly ash, such as its carbon content or presence of activated carbon or the sulfur content or the alkali content of fly ash. There has been a study that came out recently that suggests that if all stays the same, the supply of specification compliant fly ash by the year 2030 would stay at around 15 million tons, while the demand will exceed 35 million tons. So there's a large supply gap. There also has been a recent AASHTO survey of all state DOTs, and over 80% of state DOTs indicated facing issues with fly ash availability in the last 4 years. So in the 4 years that study is investigated, which was 2012 to 16. So there's clearly a supply issue with fly ash, and also there are similar issues with slag, and there is a need for alternative materials to supplement the supply of pozzolans. And two of such materials, which I'll talk about today, are FBC fly ashes or fluidized bed combustion fly ash and calcined clays. Okay, next slide, please. So I'll talk about both of these resources, which are fairly abundant in the Mid-Atlantic region. I'll introduce them, what they are, do they meet the relevant ASTM and AASHTO specifications for users' concrete pozzolan, and can they produce a good quality concrete? Okay, so next slide is the same thing. It's just I'm showing that I will start with calcined clays. The pictures, as you can see on the right, are pictures of calcined clay and an FBC fly ash. So next slide, slide number 5. So let me start by what calcined clay is. A lot of people, when they hear calcined clay, they think about methacalin, which is a kind of a niche, high-priced product, and that is based on a very high purity kaolinite clay that are calcined and ground to a high fineness, and it can have a very good impact on the properties of concrete, but it comes at a premium cost. Calcined clays are not limited to such high purity clays. We can use clays that are only 50% kaolin or even lower than that, and these can be heat treated by essentially heating them up to about 1400 Fahrenheit, and as a result of this treatment, they gain nice pozzolanic properties. In the map of the U.S., essentially the areas that we see by the orange color, which is large parts of Mid-Atlantic and southeastern United States, there is this abundance of so-called altisoils, which are highly weathered soils that are rich in minerals such as quartz, kaolinite, and iron oxide. And kaolinite is the clay mineral which has high pozzolanic potential after it's heat treated or after it's calcined. Quartz is an inert mineral, and iron oxide or hematite, which are present in few percentages, is responsible for the orange to red color. And I'll show you some of the results on the soils as they are, but we also are working on technologies to be able to separate the quartz and iron oxide, so we can, for example, improve the color and make it a product that is much more wider, as well as a product that is much richer in kaolinite, and as such, it has much higher pozzolanic properties. Slide 6. Essentially, I'm going to show if this calcined clay would meet ASTM C618 or AASHTO M295, which are equivalent specifications for the most part for users concrete pozzolan. There is a clay source in particular in Maryland near Pennsylvania border that we essentially acquired in collaboration with York Building Product, and we heat treated it, and we tested, and I'll show you the test results. Next slide, please. So here we see first we see the bulk chemistry or oxide composition of these calcined clays, and a comparison with the the AASHTO requirements. So the table at the bottom is the AASHTO requirements. These calcine clays would fall under Class N pozzolan. The AASHTO says the sum of silicon, aluminum, and iron oxide has to be minimum of 70%. And if you look at the table on the top, which is the actual results on these calcine clays, we see that the sum of these three oxides are more than 96%. So, they have very low calcium content, from a chemical standpoint, they fit a pozzolan very nicely. If we go down this table, the table on the top, we see the sulfur content is pretty low. The alkali content is fairly low. AASHTO specifies as an optional requirement of 1.5% alkali content, and this is less than half of that. And we also did some X-ray diffraction studies that shows that this calcine clay is a little bit over 50% quartz, and about 2.2% hematite, and about 45 and 0.2, or around 45% dehydroxylated or thermally altered clay. So that 45% is really the active ingredient of the pozzolan. We can go to slide number 8. So here's a table with the physical properties of these calcine clays and comparison with the AASHTO specifications. So if I go down the table, you can see moisture content is pretty low. Fineness is the AASHTO specified 34% maximum, essentially particles larger than 45 micrometer. This is only 17%, so it's a fine particle, which makes it reactive. And at the same time, it increases the water demand a little bit. Loss in ignition, LOI value is very low. We keep going down. Carbon content, very low. Particle size distribution is fairly fine. The soundness is excellent in comparison with the AASHTO requirement. The water requirement, as I said, these are fine particles. It meets the specification, but it's a little bit on the elevated side. And strand activity index is 81.6%, which is more than 75% that AASHTO requires. Now, I'm going to show you some strength results in a minute that essentially shows that good. They even improve slightly the strength of concrete when they're used. So essentially, they meet all AASHTO M295 requirements, both physical and chemical. Okay, let's go next slide. So the next question is, can we use these to produce a high-quality concrete? Next slide. So what we did is that we essentially mixed a AA paving concrete mixture with water cement ratio 0.47. The table that we have here shows the mixed proportions for a control mix as well as a test mix that had 20% of Portland cement replaced with calcine clay. And at the a few things that I can point in this table. First of all, if we look at the bottom, we see that both mixtures achieved a desired slump. In this case, the design slump was 4 inches. The air content was designed at 7%. So both mixtures achieved that. If you also look at the superplasticizer row, you can see that the test mixture required a high amount of superplasticizer, and that's because of its essentially higher water demand. Let's go next slide. So this graph shows the compressive strength of both mixtures, and we see that they both achieved and surpassed the PennDOT requirements of 3750 psi at 28 days. Actually, they're much beyond that, about 5500 psi. And we can see that the calcine clay mix is even slightly doing better than the control mix across the board, even as low as 7 days. Next slide. Here we see some results on the rapid chloride permeability test, which the small table on the left, we see that the calcine clay mix improved the RCPT value slightly, or reduced it slightly. We're going to do this also at 56 days and we believe that the mix is going to perform even better at 56 days. The graph on the right shows some ASR testing results. These were performed with a highly reactive or R2 aggregate, which is shown by the blue curve. And the other curves are when we took some cement out and added calcined clay. And you see that somewhere around 25% to 30% is sufficient to mitigate ASR induced by this highly reactive aggregate. This is according to accelerated mortar bar test. We will be doing the concrete prison test in the near future. Next slide shows the drying shrinkage, which is pretty comparable, the control versus the 20% calcined clay mix. Finally, this slide, actually, we did so slide number 14, which shows ternary mixtures. So finally, we did some ternary mixtures of, one is called an LC3, which is a limestone calcined clay cement mix. It has 15% limestone, 30% calcined clay, and 55% Portland cement. And the other one is SC3, or a slag calcined clay cement, which is 15% slag, 30% calcined clay, and 55% cement. And you can see both of these mixtures from a compressive strength standpoint. At 7 days, they are pretty comparable. They're pretty close to the control. And at 28 days, the limestone calcined clay is essentially identical to the control, to the 100% cement mix, while the slag calcined clay is significantly exceeding the strength. So essentially, calcined clay in combination with limestone and slag can be used to produce concretes that have almost half as much as Portland cement. So you can cut the cost and you can improve the durability without really losing any strength. Slide number 15. These are some essentially conclusions on calcined clays. So impure kaolinite clays that have less than 50% kaolin content can be heat treated to produce a quality concrete pozzolan. And the source of clay that we studied and we calcined showed good performance in concrete. It met all AASHTO M295 or ASTM C618 requirements. It produced a good quality concrete in terms of slump, air content, and strength. It mitigated ASR. It improved the chloride permeability or reduced the chloride permeability, and it had a similar shrinkage versus the control. And we were also able to produce ternary mixtures that have only 55% cement and the rest being essentially SCMs or supplementary cementitious materials, and they showed similar or significantly better strength than the control. We're still doing well with the voice?
Yes, we are.
Okay, fantastic. All right, so let's go to the next slide. So I'm going to shift gears and talk about FBC fly ash, and I try to kind of keep this fairly brief so we don't exceed the time. So again, we'll talk about what it is. Does it meet the ASTM AASHTO specifications, and can it produce a quality concrete? Next slide. So some of the folks that are in the audience might have heard about FBC boilers or FBC fly ashes. They are actually, Pennsylvania is one of the leading states in having this fluidized bed combustion technology for coals. And the map of Pennsylvania that we see here shows the coal sources that we have. That western part of the U.S. is essentially a home of bituminous coal reserves, and then we have some areas in the central eastern U.S. that have these anthracite coal, which is older and higher in carbon content. Now, many of these have been mined, either surface mined or underground mined, several decades ago, maybe 50, 60 years ago, and the overburden or the parts that were mixed with soil and essentially did not have a high purity coal are just deposited on the surface in the form of these waste coal piles or so-called GOB piles. And the problem, if you just keep clicking as you see the different pictures on the same slide, one of the problems that these GOB piles have is that they produce acid mine drainage. So essentially they have a iron sulfide mineral that in exposure to rain, they produce sulfuric acid, which is very bad for the environment. So if we go slide number 18, for the last maybe 2 decades, there has been these so-called fluidized bed combustion or FBC boilers, which come and take these golf pods that have about 30% fuel or 30% carbon and burn them to produce electricity, and they end up with an ash which has about 5% or less carbon content. And this ash has been for the most part, or is for the most part, surface deposited. So, if you go around these power plants, you see there are large fields of this fly ash kind of sitting on the ground. Next slide. So here's a side-by-side comparison of a kind of conventional fly ash, which is on the left, versus the FBC fly ash that is on the right. So the PC or pulverized coal boilers are the dominant type of coal power plants. And the way they work is that they pulverize coal and they burn it at temperatures up to 3,100 Fahrenheit. And as a result, they produce these sulfur oxide and nitrogen oxide emissions that requires a scrubbing. But these temperatures are high enough that the mineral matter, or essentially the clays that are intermixed with the coal, they burn down, they don't burn, they melt. And as they go up the smokestack and the flue gas, they solidify in the form of these glass spheres. And these glass spheres they have several advantages for concrete, both chemically and physically. Physically, they act as a ball bearing and they improve the workability. So now if you look at the right-hand side, the FBC boilers, they only burn at temperatures up to 1,500 Fahrenheit, and they have a better, more efficient heat transfer. They have an internal sulfur scrubbing. Essentially, they inject pulverized limestone into the boiler, and what it does is that limestone would react with the sulfur and produces gypsum, and that gypsum would end up in fly ash. Which may be a little bit of a challenge to make it work in concrete. So it's something that we have to check, and we have checked. And the other thing is these temperatures are not high enough for those clays that are intermixed with the coal to melt. So they keep their original shape and structure. They just get thermally altered and they become reactive. So as you see on the image, the particles are angular, sometimes highly porous, and as such, they will have a higher water demand, much higher water demand than a conventional fly ash. Okay, we can go to the next slide. So again, we acquired 2 sources of FBC fly ash, one from an anthracite region, one from a bituminous, the western Pennsylvania region, and we looked at, next slide, number 21, again, we looked at the chemistry of these, comparison with the AASHTO requirements. So on the top, for example, for anthracite, you see the sum of silicon, aluminum, and iron oxide is about 80%, which is kind of similar to traditional Class F fly ash. For the bituminous, the sum is about 64%, which is more similar to Class C fly ash. The SO3 content is elevated for the bituminous FBC, and that's the same issue that I mentioned, that the sulfur is scrubbed and forms gypsum that ends with fly ash, or ends up in fly ash. We'll get back to that in a minute. The alkalis are moderate level. If you go to the next slide, the physical properties, moisture content, density, fineness of them are pretty good and meeting the specification. You can see the LOI for both ashes are elevated, and we'll have to check to see if we can make good quality or well air and train concrete with these, and I'll show you some of those results in a minute. We have the carbon content. You see that, for example, for the bituminous FBC, not all of the LOI is associated with carbon. But at the same time, for that fly ash, for the bituminous fly ash, the sulfur content is fairly high, which we've seen this before again. Particle size, soundness is pretty good. The water demand is a little bit high, on the high side, but still, not exceedingly large, and or not excessively large. And the strength activity index is in the 90s, 98% for one, 93% for the other. Next slide, we did some quantitative X-ray diffraction studies to look at what are some of the minerals that are present in these fly ashes. I'm just going to go to the next slide and summarize what we learned from the QXRD. So slide 24, please. So long story short, with the XRD results is that these FBC ashes are a mixture of reactive phases and inert phases. And the top, we see the reactive phases, which are thermally altered clays, and hydrides, which is essentially gypsum, and free lime. And they make up about 75% or between 75 and 79% of the fly ash, of the mass of the fly ash. And the remaining, let's say 20 to 25% is quartz and hematites, which are non-reactive or inert phases. Next slide shows the SEM images or electron microscope images of these fly ashes. We see again they have angular particles, they have internal porosity, and that can explain that higher water demand that we measured. And again, if we click, we see a comparison with nice solid spherical fly ashes without porosity, which had usually a lower water demand. Next slide, we want to see if we can use this to produce high quality concrete. Next slide, number 27, where we have the picture of slump and air meter at the bottom. Again, we made a pavement mix, a AA mix with water cement ratio 0.47. We have a control mix, and then we have two mixtures, and each of them had 20% of either the anthracite fly ash or the bituminous fly ash. At the bottom, you see the slump and air content. Again, these were designed for 4-inch slump, 6% air, and all of them met the design criteria. So even though these fly ashes have high loss and ignition, with proper use of air entraining admixtures, and if you compare the air entrainer dosage, they are not excessive. They can be air entrained, and they can produce a good air concrete with a good air. So proper slump and air could be achieved. Next slide shows the compressive strength of the three mixtures, which we essentially see that both fly ash mixtures are, within the range as the control mixture. They get better with age. So at 56 days, essentially, they match the strength of the control. At 7 and 28 days, the anthracite fly ash is a little bit lower. The bituminous fly ash is a little bit higher. Next slide shows the ASR data. And again, this is with a highly reactive or R2 aggregate shown in the black curve. And we see that with use of either of these fly ashes, somewhere between 30 and 40%, depending on which fly ash we're talking about, we can mitigate the ASR according to the accelerated Motobar test. Next slide. So the last thing I want to show is this issue of the sulfur content and whether it causes essentially deleterious expansions. So there is an ASTM test C1038 which you create these mortar bars and cure them for 2 weeks under lime water, and you measure expansion. And so here we see a comparison of the control anthracite FBC and bituminous FBC, and we see that the expansions for all three of them are within the acceptable range. The bituminous FBC is a little bit elevated. That goes hand in hand with its sulfur oxide content. If we look at the graph on the bottom, which shows the autogenous shrinkage, we see that this property actually can be put to good use and essentially use these fly ashes as a sort of a shrinkage compensating material. So we see that 0.25% expansion or 2.24% expansion in the blue curve, but we see that kind of nicely compensated for the subsequent shrinkage that happens in essentially all concretes. All right, so last slide is the conclusions on FBC fly ashes. These are materials that are produced by burning coal, primarily waste coal, at less than 1500. It should be Fahrenheit, so it's a typo. I apologize for that. Less than 1500 Fahrenheit, and this essentially would form thermally altered clays. We looked at two sources of FBC fly ashes. They showed good performance as a pozzolan. They met, for the most part, they met the AASHTO requirements, except that some, actually both of them had elevated LOI, and one of them had a elevated sulfur oxide content. But despite these, they produced good quality concrete in terms of slump, air content, and strength, and they mitigated ASR. And as I said, these are considered waste material right now, which are just landfill, and as such, they are low cost. And finally, that elevated SO3 in the case of one of the fly ashes was found not to be deleterious with respect to causing excessive expansions. So with that, thank you very much for your time, and I would, open and appreciate if there's any questions.
What was the cementitious content of the control mixes?
They are, so let me actually guide you to the proper slide. So if we go to, for example, slide number 10, you see that the cement content is 588 pounds, which is kind of on towards the lower range of what's specified by PennDOT. The other mixes that